Hi there, welcome to this video. My name's John. I provide mathematics tuition for A-level maths, A-level further maths, 6th term examination papers and mathematics admissions tests. Warm welcome to this video where we're going to take a look at the normal approximation to the binomial distribution. So, just a few words of warning before we kick off with the content, with the main part of this video. This video is going to go into potentially quite a bit of detail. I'm going to be speaking entirely unscripted here. I've got a couple of basic notes. I've got an idea about what I want to talk about. But generally speaking, it's unscripted, so I might stumble over my words from time to time. I might even make a couple of mistakes, which I need to correct as we go through the video on the screen. But I'm going to leave all of that kind of stuff in, okay? I'm going to do minimal editing on the video. So if you don't like long-form videos, and I do expect this video to last probably in excess of half an hour. If you don't like long-form videos, don't watch this video. I will be going beyond the A-level specification at certain points in this video. I will be introducing you to ideas and concepts that you won't typically come across on your A-level maths or even A-level further maths course, potentially. This is deliberate because to explain some things properly, to justify them properly, sometimes you've got to go a little bit beyond the A-level specification material. And also, I do this deliberately because I want to introduce you to ideas that you might not have come across before, which might encourage you to go on and do further research, independent research, or to ask questions. It might stimulate a bit of discussion. Okay, so if you don't want to go beyond the specification material for your A-level maths course or A-level further maths course, this video is not the video for you. Don't watch it. Okay, so if you do have any questions, I'm not going to be able to explain everything in comprehensive detail in this video. There are going to be some details that I'm going to have to miss out. Nevertheless, if there's anything that you don't understand, please leave a comment in the comments section. Just ask for clarification on whatever it is that you're struggling with. If you want me to further down the line make a video going into more detail on something that I've mentioned in this video, just let me know. Okay, I'm always open to new ideas about things that are going to help you. As it stands, I'm kind of making these videos because these are the kinds of videos that I would have liked to have seen, had access to, when I was doing A-level maths. Okay, I was very keen when I was doing my A-level maths and further maths on being exposed to new ideas, where my teachers would mention certain things that they did at university, and things like vector spaces and things that I'd never heard about, metric spaces and things like this. I was deeply interested in that kind of stuff, and I wanted to do my own research. Now, unfortunately, at the time, YouTube didn't really exist. In fact, YouTube started, if I remember rightly, it was 2005. So I'm giving my age away now. YouTube started about a month before I finished my A-level exams. So obviously there were no such things as tutorial videos and things like that. So really, at the moment, I'm making these videos for a younger version of me. But I would rather be making these videos for people who are actually doing their A-level maths and further maths now, to help them prepare for their exams and to deepen their knowledge and understanding of mathematics. So, if you do have any ideas, any suggestions, just let me know. Things that I could be doing better. So, there's a lot of people on YouTube that do tutorial videos for A-level maths and A-level further maths, and some of them do a fantastic job. But is there anything that people, including myself, are generally missing the point on, that we're not really addressing a particular issue that we ought to be? Let me know, because I want to make these videos as effective as possible, and to help you to prepare as best you can for your exams, and if you're going on to further studies in mathematics. But always, if you've got any questions, feel free to ask any questions that you want. Okay, so the whole point of this video is to give some kind of a justification about why we use the normal distribution to approximate the binomial distribution, and also justification as to why this is a reasonable thing to do. What motivates this? So there's a couple of ways that we can look at this. We can look at this from a very kind of informal, pragmatic, practical kind of perspective. Okay, so what we can do is we can maybe have a look at binomial. We might look at the graphs of some binomial distributions, the graphs of some normal distributions, and we might notice that there is some kind of similarity there. And we might even see that the similarity is very close in certain cases. And that, from a purely practical perspective, might justify the use of a normal distribution to approximate the binomial distribution. Okay. Now, the next question, I guess, is why would we do this anyway? Why don't we just if we know the binomial distribution, the specific binomial distribution that a random variable follows, why don't we just use that? Why don't we just use the various formulae that we have to calculate the probabilities and things like that? Why do we need the normal distribution? And the answer to that is that for a binomial distribution, particularly when the n parameter becomes quite large, it becomes very difficult to calculate the probabilities exactly using the formulae. From a theoretical perspective, it's not a problem, because from a theoretical perspective, you seldom want to calculate specific probabilities anyway. But from a practical perspective, just to give an example, let's say we've got a random variable x which has a binomial distribution, and I'm going to come back to this in a second, all this notation that I'm using, but maybe you're already familiar with this. And let's say we've got the parameter n is quite a large number, maybe 5,000, and maybe 0.3 here for the probability of success. And let's say we want to calculate the probability that x is, I don't know, less than or equal to 2,340, for whatever reason. This is going to be a nightmare to calculate, okay? Even for a computer, this is going to be... I don't know how well a computer would be able to keep up with this. But it's going to be a tall order, because in the calculation of this probability, you're going to have to deal with binomial coefficients, which are going to be something like 5,000 choose, I don't know, 5,000 choose 2,112. For example, this is just one of the binomial coefficients that you're going to have to deal with, amongst other things, which means that you're going to have to calculate 5,000 factorial over 2,112 factorial times 3,888 factorial. I mean, these are absolutely astronomical numbers, unbelievably huge numbers. So it just becomes utterly impractical to do this, and unnecessary, really. There's not really any necessity from a practical perspective to know the exact value of this probability. So what we can do instead is choose a suitable normal distribution to approximate these. So if we choose y is distributed normally with certain parameters which are going to be determined soon, then we can replace this probability that x is less than or equal to 2,340 with possibly, this is something else that I'm going to come back to later in the video, possibly we could replace it with the probability that y is less than or equal to 2,340, although we might need to do just change this number a little bit to get a better approximation. I'll talk about that later in the video. And because the normal distribution is a continuous distribution and the binomial distribution is a discrete distribution, continuous distributions are easier, generally speaking, to work with. It's going to be much easier, it's going to take much less computing power to calculate this probability here, that y is less than or equal to 2,340, rather than the corresponding x probability for x. Okay, we can do this in a flash. this second probability derived from the normal distribution. It won't necessarily be exact, but for all intents and purposes, from a practical perspective, it'll be good enough. Okay, it won't be exact, but it will be good enough, and that's, for most practical reasons, it'll be more than sufficient. From a theoretical perspective, then no, obviously, something's got a binomial distribution. It's got a binomial distribution, not a normal distribution. So that's why we might choose to use a normal approximation to a binomial distribution. So what I'm going to go into now in a bit more detail is what visually we see, what gives it away visually, that there is this relationship between binomial distributions and normal distributions. And then I'm going to go into more detail. I'm going to go into a much more objective way that we can choose a particular normal distribution to match up to our binomial distribution. Okay, so we've got a bit of work to do. Let me just clear a bit of space. We don't need this stuff anymore. Okay. By the way, if you do find these videos useful that I make, please show your support by hitting the subscribe button and the like button. I don't make any money from making these videos. I say this in most of my videos, but I don't make any money from making them. I really do want to make them, to continue making them, but I can only justify making them if there's a demand for them. Okay, so if you are getting some benefit from these videos, if you would like me to continue making these videos and providing you this information for free, please let me know. Please show your support for this channel, because if there's no support, if there's no demand for my videos, then I might get bored and go off and do something else. So please hit the subscribe button, hit the like button, and if you know anybody else that might get some benefit from these videos, share them. Sharing is caring, right? Okay, so I am going to assume that you have a certain level of familiarity with binomial distributions and normal distributions. Okay, so I'm not going to... I've already done another video on normal distributions, properties of normal distributions. So if you do want to, hopefully I will have uploaded that video before I upload this one. In which case, if you want to know more about normal distributions, properties of them, go and watch that video. I haven't yet made another video on binomial distributions, but I will be doing so. And I don't know when that will get uploaded, but if I haven't uploaded it yet by the time I've uploaded this video, keep an eye out for it. But I'm not going to be going into too much detail, any more detail than I really need to, when it comes to binomial distributions and normal distributions, their basic properties. Nevertheless, if we have, just a little very quick recap, if we have x is a random variable, the discrete random variable, which is distributed binomially with parameters n and p, then we write it in this way. Okay, so n is often referred to as the number of trials, and p is often referred to as the probability of success. Now these are just interpretations for these parameters. We don't have to refer to them as the number of trials and probability of success. They are just an interpretation. Okay, we can just refer to them as the first parameter and the second parameter, for example. We don't have to necessarily apply a physical interpretation to them, but often we do. Some of the properties of binomial distributions which might be useful to us are the expectation, or the mean. The expectation, and I'm not going to go through this in this video, is calculated to be n times p. In other words, just the product of the two parameters. The variance of x is equal to n times p times 1 minus p. Okay? And let's suppose, on the other hand, that we have y, which is distributed normally, and we're going to choose, remember, a normal distribution has two parameters, mu, sigma squared, often called the mean and the variance. Again, watch my video on the normal distribution to understand why we refer to the parameters as the mean and the variance. I'll give you a clue though, it's because the mean of a normal distribution with parameters mu and sigma squared has, the mean is mu and the variance is sigma squared. So, but if we choose the parameters of this particular normal distribution to be np, and np times 1 minus p, in other words, the mean of x and the variance of x, then what we find is that provided that n is sufficiently large, that the binomial distribution, let me just change to the red pen, I don't want the blue one. The binomial distribution for x, if we look at the graph of this and the graph of y, what we'll find is that there's a very close resemblance. Now, there is obviously a fundamental difference between the two because x is a discrete probability, a discrete random variable, and follows a discrete probability distribution. Y is a continuous random variable. It follows a continuous probability distribution. But nevertheless, there is a sufficiently close resemblance between the two, which I'll illustrate roughly in a second. Now, this is on the understanding that n is going to be sufficiently large and that p is not too far away from the value of half. Okay, so if you're familiar with the appearances of binomial distributions, when p is equal to a half, you get a nice symmetric distribution. Okay, but as p gets further away from a half, let's say p is decreased and it's more like value 0.01, you'll get a very skewed distribution. Okay, and it'll look more like this. Okay, so you'll get a very high peak at the left hand side of the distribution for small values of x, of x, and you'll have a very long tail. Okay, so that's when p is, let's say, much less than 0.5. When I say much less, I mean it's getting close to 0. Obviously p can't be less than 0, and we don't really want it to be equal to 0 because of very uninteresting probability distribution. So p is going to be, it's going to be close to 0. So maybe it's, I don't know, 0.01 or 0.004 or something like that. On the other hand, as p gets closer to 1, then you get a skew in the other direction. Okay, so you'll get something that looks more like that. Okay, so you get a very long tail at the lower end of the distribution, and then it'll peak right up at the upper end of the distribution. So, but a normal distribution is symmetrical. Okay, so now there's all sorts of rules of thumb when it comes to this about what's a suitable value of n, and there's no single response to this. So basically it's when n gets sufficiently large, which means it can mean all sorts of things, but from a purely mathematical perspective, when you say that n gets large, it means that n is getting basically closer and closer to infinity. Now this is that's a mathematical interpretation. What about from a practical perspective? What would be a suitable value of n? Well, maybe it's not so much just the value of n that we've got to keep an eye on. It's more like the value of n and p, and very often it depends which resource you're using, which textbook you look in, which author you're referring to. But let's say if you've got n times p is greater than or equal to 5, then often this will give a reasonably then if you use a normal distribution, a normal approximation, you'll get reasonably good approximations. Okay. or you can expect to get reasonably good approximations, provided that n times p is greater than or equal to 5. That's not saying that you can't use a normal approximation if n times p is less than 5. It's just that the approximation is not necessarily going to be any good. But having said that, there is no necessity when we talk about approximations. There is no necessity for our approximations to be good. So I could come up with a terrible approximation, such as I'm going to approximate every binomial probability by the number 0.1627. You might think, well, why have you chosen that? Well, why not? Okay, it's going to be a hopelessly bad approximation. It's going to be practically useless, but it's still an approximation. Okay, an approximation doesn't have to be good. It's just we really do want it to have some resemblance to. If we approximate something, we do want some kind of resemblance between the approximation and the approximating thing and the approximated thing. Okay, so yeah, we may choose NP to be greater than or equal to 5. Now, it really does depend on the specific author that you refer to. What I would suggest is that you check the specification for whichever exam board you're doing for your A-level maths course. What does the specification say? Because it might vary slightly from one specification to another. Just check your specification and stick to that. Okay, just stick to that, whatever it says, and you can't go wrong. But just be aware that if you do flirt with other authors and other resources and textbooks and things like that that are not specifically for your course, the specification for your course, you may encounter conflicting information. And it's not that it's wrong, it's just that there's no general agreement about when a normal approximation should be used. Just rules of thumb. So just a warning on that. So what do we see then visually that might motivate us to realize that there is this kind of relationship between normal distributions and binomial distributions? So it's kind of difficult to draw a binomial. Oh, that's not a very straight line at all, is it? To draw a binomial distribution, it's going to be a little bit difficult actually, but I'll try. Okay, so this is my axes for the binomial distribution. So we've got x is distributed binomially. Might be worth you taking notes, by the way, because I can't leave all of the relevant information on the screen all at the same time. So if you need to take notes, do so. Okay, so up here we've got the probability of x. So the graph that I'm going to draw is of the probability mass functions, because x is a discrete random variable. It has a probability mass function. Now, there's different ways of representing this, but one common way is using a step function, or something that looks like a step function. Okay, so we've got our outcomes down here on the horizontal axis. Remember, we've only got integer valued outcomes. 4, 5, up to right at the upper end, we're going to have n minus 2, n minus 1, and then finally n. Okay, now this is going to be fun because it's not going to be easy to draw these rectangles. So I'm going to try to draw a typical graph that we might see for a binomial distribution. So what we'll get is something that, if we draw the rectangles, they kind of go up a little bit, like this. And then somewhere in the middle, we're going to get a peak. Okay. Oh, I didn't realise it could do that. Okay, we're going to get a peak. So on either side of this, it's going to be a little bit lower. And depending on the specific binomial distribution, this peak is going to occur at different values. I'm not going to specify which value it occurs at here, so we put some continuation dots in here. And then we come back down again. we end up with something like this. Okay, so we get a distribution that starts quite low, close to the horizontal. It increases. I mean, we've got rectangles. I'm using a smooth kind of motion, but we've really got these rectangles. So it goes up, 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 reaches a peak, and then it comes down, and it tails off again. Okay. So if we compare, if we've got a load of graphs of normal distributions, what we might notice is that if we overlay these normal distributions, so we've got the scales kind of match up in the right sort of way, what we might find is that our normal distribution, some of our normal distributions seem to fit very closely to the behavior of the normal of this binomial distribution. Okay, so this red here is a graph of just some normal distribution that seems to resemble the behavior, and we can do this for maybe we do this for many different binomial distributions, the graphs of many binomial distributions, and we see, yeah, in each case we can kind of find a normal distribution that seems to fit. Oh, we might even find a few. Okay, but what we want to do is to narrow it down to the best one, so to speak, inverted commas. And this is not a problem for us to do, by the way. You know, computers have no problem graphing these sorts of things, so we can easily make these comparisons, and we can see from a purely visual perspective that the normal distributions tend to kind of coincide with the binomial distribution, and hence, at least from a purely practical perspective, we're justified in using the normal distribution to approximate the binomial distribution. Okay, so that's one way that we can subjectively justify that method of approximation. But from a mathematical perspective, this is completely inadequate. Okay, if there is a relationship, we'd like to make it there between these two types of random variable, normally distributed and binomially distributed. We'd rather find out in a bit more objective sense what that relationship is. Okay, because if we're doing everything by eye, you might choose a particular normal distribution to approximate this binomial distribution, but I might choose a different one, a slightly different one. Okay, what we want to do is to make sure that we're all kind of reading off the same page. Okay, so how can we do that? Well, this is where things get a little bit more complicated. Okay, and I'm potentially going to have to introduce you to some brand new ideas. Some ideas that you may not have come across on your typical A-level maths course. Okay, so we're starting from scratch again now. So let's say we've got a new random variable, x. It's a discrete random variable, and it has two possible outcomes. Okay, so think about it as kind of flipping a coin. Okay, we flip a coin, we flip it once, and we've got two possible outcomes, heads or tails. The coin might be biased, might not be biased, whatever, but there's a certain probability of obtaining a head. Okay, so this could be modelled by what's called a Bernoulli random variable. Okay, so this might be something that you actually you have come across it before. I'll explain how in a second, but x. This is a new type of potentially new type of random variable or probability distribution. Very simple though. We've got two outcomes: success or fail. And we've got one trial basically. So we write this as Bernoulli with parameter p, where p is the probability of interpreted as a probability of success. Now this is actually a binomial distribution. It's just a very simple binomial distribution with parameters 1 and p. Okay, so think about a binomial distribution with one trial. Okay, that's a Bernoulli trial. So you have come across Bernoulli trials before. It's just you haven't called them that, probably. You'll have called them, well, you deal with the more general kind of case, which we're going to be looking at in a second. Okay, so it turns out that a sum of Bernoulli random variables. So okay, so let's say we've got x1, a series of random variables, x1, x2, x3, all the way up to xn, such that each of the xi are have exactly the same distribution, Bernoulli with parameter p. Okay. Righto. So, also if these are independent, and I'm not going to get into too much what that means, but they are independent, and there's an abbreviation for this, and it's IID, and I'm going to be using that again later on. IID means independent and identically distributed. So if all of these this x1, x2, x3, xn are all independent random variables and they're all identically distributed, then they're called IID. And if that's the case, then what we've got is that the sum of these xi's from I equals 1 to n can be shown to have a binomial distribution with parameters n and p. Remember, one of the conditions for a binomial, a random variable to follow a binomial distribution is that the trials are independent. Yeah, independent. And the probability of success on each trial is the same. Right? There's a couple of other conditions as well. So n is, you've got a fixed number of trials, so on and so forth. But the sum of xi have a binomial, follow a binomial distribution with parameters n and p. Okay, we can also figure out. Again, we've got x is distributed binomially with parameter p. We can figure out the expectation of x, which, or in other words, the mean. The expectation of x is equal to, and I might as well do the calculation. It's the sum over the possible outcomes x of x times the probability that x is equal to x. Now there's only two outcomes here, so this is very straightforward. It's 0 times 1 minus p plus 1 times p, which is equal to p. In other words, the mean, or the expected value of a Bernoulli random variable, is the value of the parameter. The variance, well, okay, before we get to the variance, let's calculate what's the expectation of the square of this random variable, which is the sum over x of x squared times the probability that x equals x, which is equal to 0 squared times 1 minus p plus 1 squared times p, which of course is just equal to p again. So then the variance of x is equal to the expectation of x squared minus the expectation of x all squared. These are not the same thing. The expectation of x squared, of the random variable x squared, is not the same as the expectation of the random variable x all squared. Okay, they're two different things. So this is equal to p minus p squared, which is equal to p times 1 minus p. So we've got the expectation, or the mean, and the variance of a Bernoulli random variable. Okay, so I'm going to have to leave that for a second, and I'm going to have to come back to it, because now we need to have a little bit of a discussion about what's called the central limit theorem. Okay, maybe I need to, I'll write it here actually. So central limit theorem. You will come across this at A level in a very watered down form. So when you come across, for example, the sample mean, x bar, when you do hypothesis testing for normal distributions, you'll be using effectively the central limit theorem in a very specific form. Okay, we need to use it in a slightly more general form here, though. Now, there's all sorts of versions of the central limit theorem. Some are more, some are very, how can I say, very general, and some are less general. Okay, so I'm not going to necessarily be presenting it in its most general form. I'm just going to be presenting the central limit theorem in a typical form, which is going to be sufficient for what we need to do. Okay, central limit theorem is of fundamental importance in contemporary mathematical statistics and statistical analysis. If you are interested, this was one of the things that my A-level maths teacher kind of mentioned when I was doing A-level maths, and it kind of caught my attention. I didn't really get round to researching it, but it was something that sounded really interesting to me at the time, and it is. It's a beautiful theorem, beautiful theorem, and it really shows the fundamental significance of the normal distribution in mathematical statistics. That so much of mathematical statistics centers around the normal distribution. Okay, the normal distribution is not just any probability distribution. It is the most important distribution. I mean, there's other important distributions, but a lot of those other important distributions are derived from the normal distribution. Anyway, beside the point. So, central limit theorem. If so I'm going to... Which letter shall I use? I'll use T. If T1, T2, T3, up to Tn is a sequence of, here it comes, IID, independent and identically distributed random variables, and I'm not making any restriction about whether they're discrete random variables, continuous random variables, or mixed random variables. They can be any type of random variable. Okay, the central limit theorem is very, even in its less general forms, it's still very general, with the expectation of Ti equal to mu less than infinity, and the variance of Ti equal to sigma squared less than infinity for each I, then T bar, which equals 1 over n, the sum from I equals 1 to n of Ti. So this is the sample mean, is approximately, and I'm just going to write it like this, approximately distributed normally with parameters mu and sigma squared over n for sufficiently large n. Or another way that we could put it is that the distribution of T bar converges. We can express it in terms of convergence, but I'm happy with this formulation. It's a bit less precise, but it will suffice for us. Okay, so we're going to be making use of the central limit theorem to justify why we're able to use the normal distribution, or certain normal distributions, to approximate binomial distributions. Okay, so let's okay. There's a couple of properties of expectations and variances that I need to highlight that maybe you've come across during your A-level studies, maybe you haven't, but I'm going to state them anyway. So if we've got a random variable, what shall I use? V. Okay, V is a random variable. In fact, maybe I shouldn't use V. Maybe I'll use W. Oh dear. W. So w is a random variable, and the expectation of a, so let a be a constant, then the expectation of a times w is equal to a times the expectation of w. Okay, and the variance, and you've got to be careful with this one, the variance of a times w is equal to a squared times the variance of w. It's not equal to a times the variance of w. This is because expectation is linear, variance is not. Okay, right. Why is this important to us? Because we know that going back to x, okay, so we're still, x is distributed by Bernoulli. Oh, sorry, the xi's. So we're going back to the xi's here. x1, x2 that I was talking about before, x3 up to xn. These are IID. xi are distributed Bernoulli with parameters p. We've already calculated the expectation of the xi's and the variance of the xi's. Okay. Right. Okay. So, so I can calculate also if I set x bar equal to 1 over n, the sum of xi from I equals 1 to n, then remember the central limit theorem. The central limit theorem tells me that the expectation of x bar is going to be equal to it's going to be equal to p, and the variance of x bar is going to be equal to p times 1 minus p over n. Okay, so where am I getting that from? I'm getting that from here. Right. The sample mean t bar, which is 1 over n, the sum of the ti's, is approximately normally distributed with mean mu. What's mu? It's the expectation of the ti's. And variance sigma squared over n. Well, sigma squared is the variance of each of the ti's. N is the number of random variables in my that I'm including in my sample mean. So this is the mu, and this is the sigma squared over n. Okay. Because I know from the central limit theorem that x bar is approximately distributed with normally with parameters p and p 1 minus p over n. Okay, but it's not x bar that I'm interested in. Okay, because x bar is 1 over n, the sum of the xi. It's just the sum of the xi's that I'm interested in. Right? So I need to figure out how that is, what the distribution of the xi's, the sum of the xi's is going to be. Well, we actually know what the distribution is. Remember, I stated it earlier, the sum of the xi's is distributed binomially with parameters n and p. Okay, but the sum of the xi, I need to clear a bit more space here. The sum of the xi's is equal to n times x bar. Okay, so that means that the sum of the xi's is going to be distributed as a normal distribution, I need to figure out what the parameters are going to be, right? Because nx bar is basically just a scaled version of x bar. So if x bar has a normal distribution, then nx bar will also have a normal distribution. And okay, so x bar has an approximate normal distribution, maybe I should say. Then nx bar will also have an approximate normal distribution. But I need to figure out what the parameters are. So how do I do that? Well, I need to use the properties of expectation and variance that I've just given. So the expectation of nx bar is equal to n times the expectation of x bar. Okay, but the expectation of x bar is p, or the mean of x bar. So this is equal to np. So the first parameter here is np. What about the variance? Variance of nx bar is equal to n squared times the variance of x bar. What's the variance of x bar? It's p times 1 minus p over n. So the n squared times the variance of x bar is going to be n squared times p times 1 minus p over n, which is np times 1 minus p. So in other words, and this is approximate, by the way, maybe I should have made that clear. So in other words, we know that sum of xi is distributed binomially. But we also know that the sum of xi is approximately distributed normally, with the indicated parameters in each case. So n and p for binomial, np times 1 minus p for the approximate normal distribution. And hence, this particular normal distribution can be used for sufficiently large n to approximate the probabilities of the binomial distribution. Okay, so that gives us a much more objective justification. Okay, so we're not quite done yet though, because as some of you will be aware, when we use the normal distribution, because a normal random variable is continuous, there's something called a continuity correction, right? Now, why do we use the continuity correction? Well, let's go for, again, x is distributed binomially with parameters n and p. Okay. And let's kind of zoom in on a particular outcome. So let's say we've got 18, 19, 20, 21, 22, whatever. Okay, and our graph looks like this for the binomial distribution. And we've got another random variable y, which is distributed normally with parameters. Oh, what's gone on here? Oh, the pen stopped working. No, I don't want that. There we go. Nope. Oh, there we go. Okay. And let me get rid of that. I clicked something on the pen and it started going crazy. On the stylus, sorry. NP 1 minus p. Okay. And let's suppose that this normal distribution kind of looks like this in comparison to the, in fact, I'd rather it go through a little bit better. if it's something like that. Okay, so we kind of zoomed right in. There might be a large value for n, so this is kind of zoomed right in. And let's say we want to calculate the probability that x is less than or equal to 19. Yeah, x is less than or equal to 19. So that means that we've got a load of rectangles up here that we're going to have to calculate the area of. We're going to have to calculate the area of this rectangle, which corresponds to 18, and also this rectangle here, which corresponds to 19. Okay. But when it comes to using the normal distribution, our normal approximation, we might naively replace this probability with the probability that y is less than or equal to 19. And what's that going to do? Well, that's going to kind of cut off here. And it's going to calculate this area to the left-hand side of this line. But then we've got this big old rectangle here that seems to have been missed off. Okay, so how can we kind of compensate for that? Well, this is where the continuity correction comes in. Okay, so think about when you round numbers. Okay, in a discrete distribution, you can't have any outcomes between 19 and 20. But with a continuous distribution, you can have all of the outcomes between 19 and 20, all of the real valued outcomes between 19 and 20. Now, as you know, anything up to 19.5 will be rounded down to 19. If you were to round to the nearest whole number, you would round down to 19. So, okay, if you really want to be nitpicky, we're not including 19.5. We're going up to, but not including 19.5. Well, all of those values, if we were to round to the nearest whole number, will round down to 19. Okay, so what would be better for us to do, potentially, to get a better approximation, is rather than replacing this probability in x with this probability in y, we replace the probability x is less than or equal to 19 with the probability that y is less than or equal to 19.5. And in that way, we end up calculating right up to... Oh, let me get rid of that as well. We end up calculating right up to 19.5. And we tend to get a better approximation. Okay. Now, we could also go in the other direction as well. So if we wanted the probability that x is greater than or equal to 21, for example, we wouldn't replace this with the probability that y is greater than or equal to 21. Rather, we'd replace it with the probability that y is greater than or equal to 20.5. Right? Because, again, any outcomes on the continuous random variable that are between 20.5 and 21 will be rounded up to 21. So in this way, we get a somewhat better approximation. Now, maybe when the value of n is very large, we don't really need to do this. It really depends. We don't have to apply the continuity correction, although maybe there will be some expectation with your A-level maths that you do apply the continuity correction. Just check with your specification to what extent you're expected to make use of the continuity correction. But there's no necessity for us to do so. Like I said earlier, an approximation doesn't have to be a good approximation. It's just, generally speaking, we would like the best approximation that we can get, within certain parameters, within certain limitations. So if applying the continuity correction gives us generally better approximations at very little extra cost, then we may as well just apply it, right? And there might also be other ways of applying continuity correction. So just like when you approximate definite integrals using rectangles or using trapezium rule or Simpson's rule, for example. There's different ways, and they will give different approximations. Different, some will be better than others in certain circumstances, and so on and so forth. But there might be, as the approximation gets better, or the method that you use gives a better approximation, it might also come at you might have to pay the price of it taking a bit more time to produce the approximation. So if you need a rough and ready approximation, maybe trapezium rule will suffice. If you've got a bit more time, maybe Simpson's rule is something that you could use. Or if you've got even more time, maybe an even better approximation. Whatever, okay? But there might be different ways of applying continuity corrections. But generally speaking, this continuity correction, it does the job. It gets you a generally better approximation at really no extra time cost. Okay, so this is the continuity correction. Okay, so I think that pretty much brings us to the end of this video. There's not really anything else that I want to talk about on this. I will be making plenty more I plan to make plenty more videos for this channel. But like I said, if you've got any ideas about anything that you'd like me to cover, just let me know. Please hit the subscribe button, hit the like button. Let me know if there's anything that you've struggled with, that you're not quite sure about. What else was I going to say? Don't know. I'm feeling very slobbish today because I'd prefer to have my shirt and tie on as I'm making these videos, but it's so hot. It's actually cooled down now because it's getting quite late, but it gets unbearably hot in this room. And you might say, well, why don't you change to another room? Because it's just not practical for me to do so. And I can't really have the window open because you'll hear the traffic and there's somebody angle grinding outside. So unless you want an angle grinding soundtrack to the video, then I've had to keep the window shut. So it's absolutely sweltering in this room. So anyway, let me know what you think about this video. There's nothing else that I want to say about this. So thank you for watching. If you made it this far into the video, congratulations. And I will look forward to seeing you in the next video. Thank you very much.